All right, well, hello physics students, and welcome to this video lecture that is meant for those of you that were not in class today due to the AP registration. Basically, what we went through at the beginning of class and the start of class today was the WebQuest that you were to work on Wednesday. So really, we just kind of picked out some select questions just to debrief and really formalize this idea of Newton's second law of rotation. So first things first, a relatively easy question that I asked you here. What is the mathematical definition of Newton's second law? I'm sure a lot of you wrote this down. We remember that F equals ma. Me personally, and I know I mentioned this in the forces unit, I prefer we write it in this form right here. Reason being is this really shows us the relationship between the variables, and it really shows us what Newton's second law is actually telling us. So when I look at this expression, what I'm seeing is that force causes acceleration, okay? And in terms of the relationship, well, we can see that acceleration and force, they have a proportional relationship. Like if we increase force, this is going to increase. But then that means that mass and acceleration have an inverse relationship. You know, if I increase mass, then acceleration decreases. So that's why I like this form here. Now, moving on to question 4. The purpose of this question was once again to say, okay, we have these linear motion variables, but we always have rotational equivalents. So I think the first couple on here were relatively easy. Rotational equivalent of force is torque, and we abbreviate that with that Greek letter tau. Rotational equivalent of linear acceleration. This one should have been pretty easy because we've already talked about this one through that rotational kinematics section that we did. So linear acceleration, rotational equivalent is angular acceleration. And that is our alpha, or fishy. And then finally, rotational equivalent of mass. That is rotational inertia, which we're going to abbreviate with an I. Okay? So there's our equivalents. Now, in 5, all we need to do then is say, okay, I know Newton's second law. I know that equation. We just now need to plug in these rotational equivalent terms. So what we're going to end up with here is we're going to say angular acceleration is equal to torque divided by rotational inertia. Once again, I like this form. A lot of you may have wrote this. I mean, this is fine. But again, I don't know if this really shows the relationship all that well. Again, what this is telling us here is that angular acceleration is caused by torque, okay? And we have a proportional relationship between these two. If this increases, fishy increases. For angular acceleration and rotational inertia here, we see that inverse relationship. So this is going to be helpful when we start trying to conceptually think through problems because we can very easily see these relationships within this expression. All right, now number 6, rotational inertia. Now, we've been working with rotational inertia throughout this week. Really, all I want us to remember for rotational inertia is that it is the resistance of an object to rotation. So, similar to the way inertia is the resistance of an object that changes motion, while rotational inertia then is the resistance of an object to rotation. Okay, now what is rotational inertia dependent on? A lot of you probably put here mass distribution, or where the mass is. And that's fine, but we need to be more specific. We need to know that it's the mass distribution in relation to the axis of rotation. Okay, so what I mean by the axis of rotation, what that object is actually rotating about. Now, I brought this up in class today, but a really tangible example of this is thinking about a figure skater doing a spin. Okay, initially they start that spin out with their arms and their limbs away from their body. The axis of rotation of that skater is running down through their body. So when their arms and their limbs are extended out, they have more mass further away from that axis of rotation. So that means they have a greater rotational inertia. But they eventually bring their limbs in, and what do we notice? Well, we notice then that they spin faster because they manipulated their rotational inertia. They brought their mass closer to the axis of rotation, therefore decreasing their rotational inertia. I encourage you to keep that example in your mind to help you kind of manipulate this idea of rotational inertia and what it means in terms of an object's rotation. All right, so to wrap this video lecture up, I just want to go through those two application questions. First, the conceptual one, and then we're going to go through the mathematical one as well. So, in this conceptual application, what we have here is we have this contraption. And initially in the first setup, those masses are completely out on the outside of that rotating platform. And now in the second condition, what's happening is there's the axis of rotation. We're moving those masses in towards the center, okay? So I want us to keep this in mind right here, because ultimately we're trying to determine what's going to happen to the angular acceleration. So if these masses get moved closer to the center, again, thinking about the figure skater, that means that my rotational inertia is going to decrease. If rotational inertia decreases, again, it's an inverse relationship, that means that the angular acceleration has to increase, okay? So because those masses move closer, more mass closer to that axis of rotation means smaller rotational inertia. All right, so now for the mathematical application, we are told in this problem that we have a meter stick of negligible mass, okay, that is able to rotate about its end, okay? But we're also told that there are masses located at 40 centimeters and at 100 centimeters. So ultimately what we're trying to do in this problem is we're trying to figure out what this angular acceleration is about that pivot, okay? But notice we don't know the torque, nor do we know the rotational inertia. So this is where I think these problems get a little more math intensive in this unit. There's just a lot of steps that we have to go through. So just to start, let's pick one of these. Let's start trying to find the torque. Well, remember that torque is force perpendicular times the lever arm. So the force that we're dealing with here that's acting on these two masses is the force of gravity. So what I'm going to say here is that the sum of my torques, okay, the reason I'm saying sum is we have 2 torques here, is going to be equal to 0.2 times 9.8. So that is the force of gravity acting on this mass times the lever arm. So in this case, for that first mass, it's going to be 0.4 meters. Plus, once again, 0.2 times 9.8, that's the force, times the lever arm, which is the full meter. Okay, so if we calculate that out, then we end up with a 2.74 Newton meter torque. All right, now for rotational inertia. We have 2 things contributing to the rotational inertia. We have these 2 point masses. And this is why I wanted you to find that equation for the moment of inertia, or the rotational inertia of point masses. So what we can say here is that we're going to say this total amount of inertia is going to be equal to that first mass times its distance. Okay, so this stands for distance from that axis of rotation, plus that second mass times how far it is away squared. So if we plug this stuff in, this is what it's going to look like. And we are going to get a rotational inertia here of 0.232 kilograms times meters squared. Okay, if you take a look, these units should make sense because here we have mass and here we have a length. So kilograms times meters squared. All right, so we're almost done. What we're going to do is we're going to take this value and plug and chug it into here. So this is going to look like this. 2.74 Newton meters divided by 0.232 kilograms times meters squared. That's going to then give us, for a final answer, 11.8 radians per second squared for that angular acceleration. Okay, so there's what we covered in the first part of class today. We went through this WebQuest, making sure that we're all on the same page, and tried to start applying this idea of Newton's second law of rotation. So, hope this was helpful. This should get us going pretty well for the lab that we're going to start tomorrow. See you, physics students. Take care.